Learning objectives. In this chapter, the user would learn the following in detail: introduction, discrete random variable, distribution function, probability mass function, Bernoulli and binomial random variables, continuous random variables, probability density function, uniform random variables, moments and expectation, jointly distributed random variables, independent random variables, covariance and correlation, expectation of sum of random variables, Markov and Chebyshev inequalities. Discrete and continuous random variables. A variable is a quantity whose value changes. A discrete variable is a variable whose value is obtained by counting. Examples: number of students present, number of red marbles in a jar, number of heads when flipping 3 coins. Students' grade level. A continuous variable is a variable whose value is obtained by measuring. Examples: height of students in a class, weight of students in class, time it takes to get to school, distance traveled between classes. A random variable is a variable whose value is a numerical outcome of a random phenomenon. A random variable is denoted with a capital letter. The probability distribution of a random variable x tells what the possible values of x are and how probabilities are assigned to those values. A random variable can be discrete or continuous. A discrete random variable x has a countable number of possible values. Example: let x represent the sum of 2 dice. The probability distribution of x is as follows. A continuous random variable x takes all values in a given interval of numbers. The probability distribution of a continuous random variable is shown by a density curve. The probability that x is between an interval of numbers is the area under the density curve between the interval endpoints. The probability that a continuous random variable x is exactly equal to a number is 0. Means and variances of random variables. The mean of a discrete random variable x is its weighted average. Each value of x is weighted by its probability. X is equal to x1 p1 plus x2 p2 plus etc. At the end plus xk pk equal to summation xi pi equal to expectation of x. It is denoted by E of x. To find the mean of x, multiply each value of x by its probability, then add all the products. The mean of a random variable x is called the expected value of x. Let x be a discrete random variable, then the nth moment of x is denoted by mu dash n and defined as mu dash n is equal to expectation of xn, where E denotes the expectation function, that is mu dash n equal to summation x belongs to O, then x and then small x, np, capital X of x. Whenever the sum converges absolutely, it can be seen from its definition that the expectation of a discrete random variable is its first moment. Also, see the relation between the variance of a discrete random variable and its second moment. Bernoulli random variable. Suppose you perform an experiment with the two possible outcomes, either success or failure. Success happens with probability, while failure happens with probability. Bernoulli random variable. Suppose you perform an experiment with two possible outcomes, either success or failure. Success happens with probability, while failure happens with probability. Continuous random variable. A continuous random variable can take any values in an interval. Example: f of x is equal to 3x square for 0 less than x less than 1 equal to 0 otherwise. For any continuous random variable with the probability density function f of x, we have that integral minus infinity to infinity f of x dx equal to 1. This is a useful factor. Example: x is a continuous random variable with the probability density function given by f of x equal to cx for 0 less than or equal to x less than or equal to 1, where c is a constant, find c integral c 0 to 1 x dx equal to 1. Then after solving the integration we getting c equal to 2. Solution: if we integrate f of x between 0 to 1, we get c by 2, hence c by 2 equal to 1 from the useful fact above, giving c equal to 2. A continuous random variable x is said to follow a uniform distribution with parameters a and b. Written, x follows uniform distribution of a comma b if its probability density function is constant within a finite interval in closed interval a comma b and 0 outside this interval with a less than or equal to b. The uniform distribution has expected value e of x equal to a plus b by 2 and variance b minus a whole square divided by 12. Continuous probability distribution. If a random variable is a continuous variable, its probability distribution is called a continuous probability distribution. A continuous probability distribution differs from a discrete probability distribution in several ways. The probability that a continuous random variable will assume a particular value is 0. As a result, a continuous probability distribution cannot be expressed in tabular form. Instead, an equation or formula is used to describe a continuous probability distribution. Jointly distributed random variable. Definition: x and y are jointly distributed random variables if x and y are both random variables defined on the same sample space S. Definition: x and y are discrete jointly distributed random variables if they both have a countable set of possible values x1, x2, etc. and y1, y2, etc. In this case, the joint probability mass function of x and y is p of xi, yj equal to p of x is equal to xi given y is equal to yj. X and y each have their own probability mass function, which are usually written p of x is equal to x, p of y equal to y, and are called the marginal probability mass functions of x and y. The joint probability mass function of x and y may be written as summation ij p of xy of xi, yj equal to 1. Example: two cards are dealt from a shuffled deck. Let x be the number of these cards, which are spades, and y be the number of hearts. Find the joint probability mass function of x and y. Joint probability distribution. A joint probability density function for the continuous random variables x and y, denoted as f of x, y, satisfies the following properties. Number 1. F of x, y greater than or equal to 0 for all x and y. Number 2. Integral minus infinity to infinity, again integral minus infinity to infinity, f of x, y dx dy equal to 1. Number 3. For any range or of two-dimensional sample space, probability of x, y belongs to R equal to integral minus infinity to infinity, again integral minus infinity to infinity, f of x, y dx dy. The probability that x, y assumes a value in the region R equals the volume of the shaded region. Joint probability density function for the length of different dimensions of an injection molded part. Marginal probability distribution. If the joint probability density function of continuous random variables x and y is f of x, y, the marginal probability density function of x and y are f of x equal to integral under ry f of x, y dy, and f of y equal to integral under rx infinity f of x, y dx. In marginal we use for x y, for y we use x, where rx denotes the set of all points in the range x, y, for which x is equal to x, and ry denotes the set of all points in the range of x, y for which y is equal to y. A probability involving only one random variable, example, probability of a less than x less than b, can be found from the marginal probability of x or from the joint probability distribution of x and y. Bernoulli random variable. A discrete random variable that denotes the number of success in a finite number of trials of an experiment consisting of only two outcomes in each trials. Success or failure is called a Bernoulli random variable. Definition. Let x be a discrete random variable. Let its support be. Let we say that as a Bernoulli distribution with parameter if its probability mass function is. Definition. A random variable having Bernoulli distribution is also called a Bernoulli random variable. Note that by the above definition, any indicator function is a Bernoulli random variable. Binomial random value. A binomial random variable is the number of success in a series of trials. For example, the number of heads occurring when a coin is tossed 50 times. A discrete random variable x is said to follow a binomial distribution with parameters n and p. Written x follows binomial distribution of n comma p or bi of n comma p if it has probability distribution p of x is equal to x equal to ncx p power x 1 minus p whole power n minus x, where x is equal to 0, 1, 2 etc. n is equal to 1, 2, 3 etc. p is equal to success probability where 0 less than p less than 1. ncx equal to n factorial divided by x factorial into n minus x factorial. Binomial n is equal to 10, p is equal to 0.25. Probability density function. Random variables. A random variable is defined as a function that associates a real number, the probability value, to an outcome of an experiment. In other words, a random variable is a generalization of the outcomes or events in a given sample space. A random variable in probability is most commonly denoted by capital X, and the small letter x is then used to describe a value to the random variable. For examples, given that you flip a coin twice, the sample space for the possible outcomes is given by the following. Sample space S is equal to head head, head tail, tail head, tail tail. These are the four possible outcomes. There are four possible outcomes as listed in the sample space above, where H stands for heads and T stands for tails. The random variable x can be given by the following. To find the probability of one of those outcomes, we denote that question as probability of x equal to x, which means that the probability that the random variable is equal to some real number x. In the above example, we can say let x be a random variable defined as the number of heads obtained when two coins are tossed. Find the probability that you obtain two heads. So, now we have been told what x is and that x equal to 2. So, we write the above information as probability of x equal to 2. Since we already have the sample space, we know that there is only one outcomes with the two heads. So, we find the probability as probability of x equal to 2 equal to 1 divided by 4. We can also simply write the above as p of x equal to 1 by 4. From this example, you should be able to see that the random variable x refers to any of the elements in a given sample space. Types of random variable. Discrete random variable, continuous random variable. Discrete random variable. The word discrete means separate and individual. Thus, discrete random variables are those that take on integer values only. Summation p of x equal to 1. A quick example is the sample space of any number of coin flips. The outcomes will always be integer values and you will never have off heads or quarter tails. Such a random variable is referred to as discrete. Discrete random variables give rise to discrete probability distributions. For example, if a coin is tossed 3 times, the number of heads obtained can be 0, 1, 2 or 3. The probabilities of each of these possibilities can be tabulated as shown. Number of heads 0, 1, 2, 3. Probability 1 by 8, 3 by 8, 3 by 8 and 1 by 8. Sample space equal to H, T, H, T, H, H, T, T, H, 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 T, H, T, 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 H, T, 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 T. H stands for head, T stands for tail. A discrete variable is a variable which can only take a countable number of values. In this example, the number of heads can only take 4 values 0, 1, 2, 3 and so the variable is discrete. The variable is said to be random if the sum of the probabilities is 1. For every x belongs to S, there exists y belongs to y such that f of x equal to y. Continuous random variable. Continuous is the opposite of discrete. Continuous random variables are those that take on any value, including fractions and decimals. Probability of 1 by 4 less than or equal to x less than or equal to 1 by 2 equal to probability of x belongs to 1 by 4 comma 1 by 2 in the closed interval equal to integral 1 by 4 to 1 by 2 f of x dx equal to integral 1 by 4 to 1 by 2 2x dx. After integrating, we getting 3 by 16. Continuous random variables give rise to continuous probability distributions. From events to random variable, concise way of specifying attributes of outcomes, modeling students, grade and intelligence. Ohm is equal to all possible students. What are events? Very cumbersome. We need functions that maps from Ohm to an attribute space. Probability of G equal to A equal to probability of student belongs to Ohm. G of student equal to A. Independent random variable. Two random variables are independent if they convey no information about each other and as a consequence receiving information about one of the two does not change our assessment of the probability distribution of the other. This lecture provides a formal definition of independence and discusses how to verify whether two or more random variables are independent. Two random variables and are said to be independent if and only if from 52 cards, which is the probability of getting a king or a queen with replacement. P of A B is equal to P of A into P of B equal to 4 by 52 into 4 by 52. Then probability of x belongs to A intersection y belongs to B equal to probability of x belongs to A into probability of y belongs to B. In other words, two random variables are independent if and only if the events related to those random variables are independent events. The independence between two random variables is also called statistical independence. Discrete random variables. Random variables is denoted by RVS, which may take on only a countable number of distinct values. Example, the total number of tails x you get if you flip 100 coins. Random variables which may take on only a countable number of distinct values. X is a random variable with arbitrary k if it can take on exactly one value out of x1, x2 up to xk. Probability of discrete random variable. Probability mass function is denoted by PMF. Probability of x is equal to xi. Easy facts about PMF. Summation P of x is equal to xi equal to 1. Then probability of x is equal to xi intersection x is equal to xj equal to 0 if I not equal to j. Then probability of x is equal to xi union x is equal to xj equal to probability of x is equal to xi plus probability of x equal to xj. If I naught is equal to j, then probability of x is equal to x1 union x is equal to x2 union etc. At the end x is equal to xk equal to 1. A random variable x takes the values 1, 2, 3 etc. and probability of x is equal to n equal to 1 by 2n, n is equal to 1, 2, 3 etc. Covariance, a measure of the degree to which returns on two risky assets move in tandem. Covariance of x comma y equal to summation I equal to 1 to n xi minus x bar into yi minus y bar divided by n minus 1. Covariance of x1 x2 equal to sigma 1 2 equal to double integral x1 minus expectation of x1 into x2 minus expectation of x2 into f12 x1 x2 dx1 dx2. A positive covariance means that asset returns move together. A negative covariance means returns move inversely. One method of calculating covariance is by looking at return surprises, deviations from expected return in each scenario. Another method is to multiply the correlation between two variables by the standard deviation of each variable. Possessing financial assets that provide returns and have a high covariance with each other will not provide very much diversification. Example 1. If stock A's return is high, whenever stock B's return is high, and the same can be said for low returns, then these stocks are said to have a positive covariance. Example 2. If an investor wants to portfolio whose assets have diversified earnings, he or she should pick financial assets that have low covariance to each other. Probability density function. Probability density function or density function of a continuous random variable is a function that describes the relative likelihood for this random variable to take on a given value. The probability of the random variable falling within a particular range of values is given by the integral of this variable's density over that range. Example, given the PDF of a continuous random variable x as follows: f of x equal to kx into 1 minus x for 0 less than x less than 1, 0 otherwise. The probability density function is non-negative everywhere and its integral over the entire space is equal to 1. Further, confusion of terminology exists because density function has also been used for what is here called the probability mass function. Correlation. Correlation is a scaled version of covariance. Note that the two parameters always have the same sign, positive, negative or 0. R is equal to n into summation xy minus summation x into summation y divided by square root of n into summation x square minus summation x whole square into square root of n into summation y square minus summation y whole square. Correlation. When the sign is positive, the variables are said to be positively correlated. When the sign is negative, the variables are said to be negatively correlated, and when the sign is 0, the variables are said to be uncorrelated. Correlation is computed into what is known as the correlation coefficient, which ranges between -1 and +1. Perfect positive correlation. A correlation coefficient of +1 implies that as one security moves either up or down, the other security will move in lockstep in the same direction. Alternatively, perfect negative correlation means that if one security moves in either direction, the security that is perfectly negatively correlated will move in the opposite direction. Note also that correlation is dimensionless since the numerator and denominator have the same physical units, namely the product of the units of x and y. If the correlation is 0, the movements of the securities are said to have no correlation, they are completely random. In real life, perfectly correlated securities are rare, rather you will find securities with some degree of correlation. The distribution function d of x, also called the cumulative distribution function CDF or cumulative frequency function describes the probability that a variate x takes on a value less than or equal to a number. The distribution function is therefore related to a p of x. The distribution function d of x, also called the cumulative distribution function CDF or cumulative frequency function, describes the probability that a variate x takes on a value less than or equal to a number. It describes the probability that a real valued random x with a given probability distribution will be found at a value less than or equal to x. In the case of a continuous distribution, it gives the area under the probability density function from minus infinity to x. Cumulative distribution functions are also used to specify the distribution of multivariate random variables. The cumulative distribution function of a real valued random variable x is the function given by f of x equal to probability of x less than or equal to x, where the right hand side represents the probability that the random variable x takes n a value less than or equal to x. The probability that x lies in the semi-closed interval a comma b, where a less than b is therefore probability of a less than x less than or equal to b equal to f of b minus f of b into a. In the definition above, the less than or equal to sign is a convention, not a universal used one. Example, Hungarian literature uses less than but is important for discrete distributions. Hungarian literature uses f of x equal to probability of x less than x only for the continuous function but not for a discrete function. The proper use of tables of the binomial and Poisson distribution depends upon this convention. Moreover, important formulas like Paul-Levy's inversion formula for the characteristic also rely on the less than or equal formulation. If treating several random variables x, y, etc., the corresponding letters are used as subscripts, while if treating only one, the subscript is usually omitted. F of x equal to minus infinity to x f of x dx. Capital F is called cumulative distribution function and then small f is called probability density function. It is conventional to use a capital F for a cumulative distribution function in contrast to the lowercase f used for probability density functions and probability mass functions. This applies when discussing general distributions. Some specific distributions have their own conventional notation. For example, the normal distribution. The CDF of a continuous random variable x can be expressed as the integral of its probability density function f of x as follows: fx of x minus infinity to x, that is called integral minus infinity to x fx of t dt. In the case of a random variable x which has distribution having a discrete component at a value b, p of x equal to b equal to fx of b minus limit x tends to b fx of x. If f of x is continuous at b, this equals 0 and there is no discrete component at b. Uniform random variable. The values of a uniform random variable are uniformly distributed over an interval. For example, if buses arrive at a given bus stop every 15 minutes and you arrive at bus stop at a random time, the time you wait for the next bus is to arrive could be described by a uniform distribution over the interval from 0 to 15. A discrete random variable x is said to follow a uniform distribution with parameters a and b. Written, x follows uniform distribution of a comma b if it has probability distribution p of x equal to 1 divided by b minus a, where x equal to 1, 2, 3, etc. till n. A discrete uniform distribution has equal probability at each of its n values. Moments and expectations. The definition of the expectation of a random variable can be motivated both by the concept of a weighted average, and through the use of the physics concept of center of gravity or the balancing point of a distribution of weights. We first examine the case of a discrete random variable and look at a problem involving the balancing point concept. Let us now see a new concept, namely mean or average of a random variable. Consider a discrete random variable x which assumes n values x1, x2, etc. up to xn. Assume that we repeat the experiment represented by x n times and let m1, m2, etc. mn be the number of times that x1, x2, etc. xn occur. So, the mean or average value of x can be given as n tends to infinity. It tends to the probability of xi, namely p of xi is equal to pi. So, the mean or average of a random variable is, the mean value is also called as expectation or stochastic average or ensemble of x, namely e of x. Expectation of x equal to summation x into p of x equal to x. Definition of e of x. For discrete random variable, the mean or expected value of a discrete random variable is provided the series is absolutely convergent. Definition of expectation of x. For continuous random variable, the mean or average or expected value of a continuous random variable with the density function f of x is provided the integral is absolutely convergent. E of x equal to integral minus infinity to infinity f of x dx. We will get the answer. Moments and expectations. Though mean or expectation is a significant number representing the behavior of a random variable, it is not adequate to describe the behavior of a random variable completely, because two different random variables can have the same average but the sample deviations may be different. A1, A2 is equal to two sets of different but the average may be same. A1 equal to 4 elements, A2 equal to 2 elements. A1 is equal to A2 but average may be same. So to completely define a random variable, we have to find some more numbers other than the mean of the random variable. Chebyshev's inequality is another powerful tool that we can use. In this inequality, we can remove the restriction that the random variable has to be non-negative. As a price, we now need to know additional information about the variable finite expected value and a finite variance. In contrast to Margot, Chebyshev allows you to estimate the deviation of the random variable from its mean. A common use of it estimates the probability of the deviation from its mean in terms of its standard deviation. Generalized Chebyshev inequality. A more general Chebyshev inequality bounds the deviation from mean to any constant a given a positive constant a. Probability of x minus expectation of x greater than or equal to alpha less than or equal to 1 by alpha square into variance of x. Proof of Chebyshev inequality. The proof of this inequality is straightforward and comes from a clever application of Margot inequality. As discussed above, we select. Using it, we get f of x equal to modulus of x minus e of x whole square. Probability of x minus expectation of x greater than or equal to alpha equal to probability of x minus expectation of x whole square greater than alpha square. Probability of x minus expectation of x whole square greater than or equal to alpha square less than or equal to alpha square less than or equal to 1 by alpha square expectation of x minus expectation of x whole square. We used the Margot inequality in the second line and used the fact variance of x equal to expectation of x minus expectation of x whole square. Probability mass function. Probability mass function is a function that gives the probability that a discrete random variable is exactly equal to some value. The probability mass function is often the primary means of defining discrete, and such functions exist for either scalar or multivariate whose domain is discrete. A probability mass function differs from a probability density function in that the later is associated with continuous rather than discrete random variables. The values of the later are not probabilities. As such, a PDF must be integrated over an interval to yield the probability. In formal terms, the probability mass function of a discrete random variable x is a function p of x or tends to closed interval 0, 1 such that p of x equal to probability of x equal to x for every x belongs to R, where p of x equal to x is the probability that the realization of the random variables x is equal to x. Example, suppose a random variable can take only 3 values 1, 2 and 3, each with equal probability. Its probability mass function is probability of x less than or equal to probability of x equal to 1 plus probability of x equal to 2. Then 1 by 3 plus 1 by 3 equal to 2 by 3. So probability of x less than or equal to 1 is equal to probability of x equal to 1 equal to 1 by 3. Then the final answer 1 by 3 for x equal to 1, 1 by 3 for x equal to 2, 1 by 3 for x equal to 3, then 0 otherwise. Conclusion. In this chapter, we have covered the following in detail. Introduction, discrete random variable, distribution function, probability mass function, Bernoulli and binomial random variables, continuous random variables, probability density function, uniform random variables, moments and expectation, jointly distributed random variables, independent random variables, covariance and correlation, expectation of sum of random variables, Markov and Chebyshev inequalities.